And then the rest of us can mute and let Mark, our guest speaker, do his thing, talking about aerodynamics of the Canard. Sound like a plan?
Sounds good to me.
Good to me.
Okay.
Yep.
So thanks for inviting me to give a little presentation here, and I'm happy to take questions as we go along. You don't have to wait till the end. Either wave your hands around or just unmute and yell. I'm fine with that. In talking to Geneva, I had a number of different presentations I could give, and the one that hopefully all you guys settled on and were looking for was one on Canard aircraft aerodynamics and what the difference is between Canard aircraft and conventional configuration aircraft. Hopefully, are there any Canard flyers in your EAA chapter? Does anybody know?
I think there are some, but maybe not on the call.
Right.
Okay.
And I don't think.
It used to be.
Used to be.
Used to be.
All right. Well, so what am I going to talk about? First, I'll just give a little bit about my background so you have some idea of who's yakking at you. Then we'll talk about general aircraft aerodynamics, conventional and Canard. A lot of the basics are the same. It's not like Canard airplanes operate on some different universe of physics than conventional aircraft do. So there's an awful lot that's the same. We'll talk a little bit about the winglets. Most of the Canard aircraft that are flying these days have winglets at the tips of the main wing, and we'll talk a little bit about them and why they're there and how they work. We'll also talk a bit about the relative efficiency and performance and capability of Canards versus conventional planes. And there's a number of topics there having to do with whether or not they're more efficient or whether the performance is better. And then I'll go over a bit of, this presentation was originally put together for a group of Canard flyers at a fly-in in Columbia, California, up north of you guys. And so everybody there, almost everybody there flies Canards. So there was, I put together an incomplete list of modifications of Canard planes and what the effects of those modifications are. And as I said, be a Q&A at the end, but you're welcome to ask questions as we go along as well. So what's my background? My biography and my resume are online if anybody's interested, but just for short, I built a Quickie Q2 back in 1980 to 1985. I never flew that plane, but the third owner of it did fly it, and it didn't kill him, so I was very happy about that. I built Cozy Mark IV, number 386, which is November 839 Zulu. And as of today, it has about 1,691 hours on it. I also started and administer the unofficial Cozy Builders webpage and Cozy Builders mailing list that has somewhere in the neighborhood of 775 members on it. About 200 to 300 flyers, and 300 people who are building. If you guys aren't asking questions, if you could mute yourselves, because we're hearing noise in the background. Thanks. And I also run my own company called Burnside Aerospace, and I provide experimental amateur-built Canard and conventional A&P services. I am an A&P. I do pre-buys, pre-sales, condition inspections, builder assistance, modifications, upgrades, sales assistance, etc. And I also do some consulting, both A&P and engineering consulting for a couple of commercial clients, generally with regard to Canard composite aircraft. I do have a couple of degrees in aeronautical engineering from way back in the distant past. I also provide unofficial technical support for Cozy aircraft and other Canards to anybody who finds my email address and sends me a question. So let's talk a little bit about lift generation. Subsonic here, because I don't think any of us are currently flying supersonic experimental aircraft. So what generates lift? What generates lift is airflow over a surface, and you get a relatively higher pressure underneath that surface and a relatively lower pressure above it, and it creates an upward force due to the differential between the pressures. This picture that you're seeing here with motion in it, those are streamlines and air particles. So you can see that some of the lines go below the wing, some of them go above the wing, and you can see that the air going above the wing is going faster than the air going below the wing. And from Bernoulli, we know that as the velocity increases, the pressure decreases. And so this is part of the reason for why the pressure on the top is lower, is it's going faster. It's got a longer distance to travel. Now, some people think that it's going faster because it has to reach the trailing edge of the wing at exactly the same time as the air going underneath. And that's not the case at all. You can watch those dots and you can see that the air going over the top of the wing reaches the trailing edge long before the air that was going underneath the wing reaches the trailing edge. There's no requirement for equal transit times, and that has nothing to do with why the air is going faster and why the pressure difference exists. You also hear a lot about people talking about downwash aft of the wing and the effect that that has. But what you can see here is that in subsonic flow, because we're not going faster than the speed of sound in the medium and pressure waves can move forward, there's actually upwash ahead of the airfoil as well. You can see that ahead of the airfoil, the streamlines are coming in straight, and then they start heading up towards the airfoil, and then behind the airfoil, they start heading down. And the stagnation point, which is where the air hitting the airfoil basically stops at one infinitesimally small place, that's called the stagnation point, and that is below the leading edge. Now, if you take a look at very easies, long easies, cozies, velocities, any Canard aircraft, you'll generally see vortilons on the leading edge of the main wing. They're there for various purposes, but they want to be in the position of the stagnation point, and that's why you generally see them below the top surface, towards the bottom and underneath the wing. So the second picture here is a graph of the far field pressure. And you can see the airplane's relatively small, but that airplane moving through the air actually creates a very large area of increased pressure that spreads out reasonably far away from the aircraft. The pressure difference over the wings is very small, but because the wings are large, that adds up to the weight of the aircraft, and the aircraft stays in the air. So again, a little bit more on lift generation. What are the forces on the airfoil? The main one that we want is lift. And lift is defined as the force on the airfoil that's perpendicular to the flow direction. There's also drag, which we don't want, but it comes with the territory. And drag is defined as the force in the flow direction. So it doesn't matter what the angle of the airfoil is to the flow. The lift is always perpendicular to the flow, and the drag is always parallel to the flow. Those forces are intrinsic in finite airfoils, meaning three-dimensional airfoils, which is all any of us have, because our airfoils do not have an infinite span. If you could theoretically create an infinite span airfoil, then it wouldn't have any induced drag, but obviously that can't exist. But what you can think of as gliders, and why gliders have very long, skinny wings, is the longer the span of the airfoil, the lower the drag. And so you can have gliders that have lift-to-drag ratios up in the 70-to-1 range. And that's because they have very, very high wingspans. Now, there are airfoil shape effects. We're all used to seeing a regular airfoil that has a curved top and a less curved bottom. But if you take a look at aerobatic airplanes, ones that fly upside down just as good as they fly right side up, they will have exactly the same curvature on the top of the wing as on the bottom of the wing. And they'll fly exactly the same upside down or right side up. Most of us don't fly a lot upside down, so we have airfoils that are curved on the top and relatively flat on the bottom. However, pretty much anything is an airfoil. If you stick your hand out of your car window while you're driving down the highway, and you tilt it up a little bit, you'll feel a force in the upward direction. Your hand is hardly a perfect airfoil, but it will create a force. And you can see in the graph on the lower right, the different airfoil shape effects that occur. You can see the flat plate works reasonably well. It'll create a maximum lift coefficient of about 0.7, give or take, before it stalls. Then you start getting into different airfoils that have curved tops and relatively flat bottoms. And you can see that they can create much higher lift coefficients. And so that's generally why the airfoils have the shape that they have, is so that they're more efficient and they can create a higher lift coefficient, and then you can fly slower. And generally you want to fly slower so you can land and take off at lower speeds. Excuse me. So angle of attack is something that isn't always well understood. You've got a direction of flight, which is the direction the airplane is moving in the air mass. The angle of attack is the difference between the direction of flight and the chord line of the airfoil. It has nothing to do with whether you're level, or you're climbing, or you're descending, or turning. It only has to do with the difference between the direction of flight and the chord line of the airfoil. So you can see in a climb, we may be pointing up at a 30-degree angle and climbing at a 24-degree angle, but the chord line to velocity vector is 6 degrees, so that's our angle of attack. In level flight, we may be moving perfectly level in a level direction with the airfoil tilted up at 6 degrees and still 6-degree angle of attack. Same thing in a descent. We could be descending at 36 degrees, but because the airfoil is at a 6-degree angle to that direction of flight, we have a 6-degree angle of attack. So what's a stall? Laymen generally think that a stall is when a wing loses all lift and the airplane just falls out of the air. That is not what a stall is, and it's not what happens. A stall is really defined as the critical angle of attack where the lift stops increasing as you continue to increase your angle of attack. It doesn't go to zero or disappear. And in a stall, you may still have a very high lift coefficient beyond the critical AOA. You can see in the top right, there's a graph of lift versus angle of attack. It reaches a maximum at a lift coefficient of about 1.6, give or take. But even as you move 5 degrees or 10 degrees higher than that critical angle, you're still developing a lift coefficient of greater than 1. So there's still a fair amount of lift being created by the wing. It's just not enough to keep you from descending because you're not going fast enough to make sure that the lift is equal to the weight of the aircraft. So in some ways, getting above the stall speed is similar to the backside of the power curve, and that you've got something that's decreasing as you go higher rather than increasing. You can also see the red curve of drag, which increases greatly at very high angles of attack. And a stall occurs when the upper surface gets a substantial amount of surface flow. And in the picture on the right, you can see, first of all, one of the things you can see is that just below the leading edge, you can actually see one of the streamlines just sort of coming to a stop and not going up above the wing and not going down below the wing. That's the stagnation point. So at a high angle of attack, the stagnation point is fairly well below the leading edge. You can also see that the air is separating from the top surface, not very far behind the leading edge at all, and causing large eddies and turbulent flow. I'm going to try and play this little video down in the lower left. I don't know if that'll work. It does. So what you can see here is a raccoon. It's got a bunch of tufts on the wings, and they're going to stall wing, and it's going. You'll be able to see the tufts start flapping in the rings as the airflow separates over the top. And you can see it starts at the trailing edge, and the tufts are starting to flap around. And then as the airplane gets slower and slower, the angle of attack gets higher and higher, you can see that the tufts moving further forward are starting to wave around a lot more. You can see the canard in the upper part of the video The Canard also has some separation from the other and the I'm sorry, Doug?
The volume of the video is way too loud.
Too loud.
Yeah.
I'll mute it. You don't really need to hear the engine.
Thank you.
You bet. Sorry about that. So again, they're just going to go through another stall here. I'll stop it after this one. But you can see on the Canard that in a Canard airplane, you want the Canard to stall first. You don't ever want the main wing to fully stall. And that's why on the main wing, you don't see the separation moving far forward. But you will see that on the Canard, where you can really see the tufts flapping around, going all the way forward on the Canard. So talk a little bit about aspect ratio. The aspect ratio of the wing is the ratio of the span squared to the wing area. On very simple wings, it's just the span over the chord. Gliders, as we mentioned earlier, have very high aspect ratios because that reduces their drag. General aircraft are generally low to medium aspect ratios, like a Piper Cherokee shown there is 5.5, give or take. Delta wing and supersonic aircraft are very low, generally very low aspect ratios. And most of the Canards out there, like I said, long easies, very easies, cozies, the aspect ratio is about 8. So what's the effect on the lift curve slope of aspect ratio? Well, the infinite aspect ratio, which is equivalent to infinite span and 0 drag, also has a lift curve slope of 2 pi, which means that as you increase the angle of attack, the lift coefficient will go up by 2 pi times the angle of attack. As you lower the aspect ratio, you get a lower slope. And so what that means is that in order to get to the same lift coefficient, you have to go to a much higher angle of attack at lower aspect ratios. Now you always want the front wing, and this is on any plane, whether it's a conventional plane or a Canard, you always want the front plane to have a lower lift curve slope than the rear wing, because that contributes to pitch stability. But on the other hand, you want a higher lift curve slope than the rear wing so that you have deep stall resistance. So on Canard aircraft, the designer's job is to balance the two opposing needs. Then there's also wing sweep, and there's 3 types. No sweep, like you have on a Cherokee or a Cessna 172 or an RV. You can be swept back, like on essentially all commercial airliners and most Canards, or you can sweep forward. And aerodynamically, sweeping forward and sweeping aft are pretty similar. The sweep has a similar effect as aspect ratio in that as you increase the sweep, you decrease the lift curve slope. So this works in concert with the aspect ratio to ensure the stability of the plane. You can tweak the sweep, you can tweak the aspect ratio. Aft swept wings are structurally stable, meaning that as they try to twist while they're flying, they will twist in a way that reduces the load on the wing. The problem with forward swept wings, and why you don't see them very often, is that they are structurally unstable, meaning that as they try to twist, they're trying to twist in a way that will increase the lift on the wing, which will cause them to try to twist more, which will cause there to be more lift, et cetera, et cetera. If they're not stiff enough, that can become structurally unstable and lead to divergence or flow. So what does pitch stability mean? There's 2 different kinds. There's static and dynamic. In static stability, the question is, does the airplane want to return to its trimmed airspeed? You're flying along, you trim for some speed, let's say 120 knots indicated, and you push a little forward on the stick and you let go. What does the airplane do? Does it eventually try to return back to 120 knots indicated? Does it just stay in whatever attitude it was that you pushed to? Or does it actually keep increasing its speed and pointing more nose down? Or conversely, if you pull back on the stick, does it continue to try to climb? So static stability just means that it will try to, if it is statically stable, it'll try to return to whatever your trimmed airspeed was. And that is what you need to have in order to have a safe airplane. Dynamic stability involves oscillations after a disturbance. So let's say you push your stick a little bit forward and the plane starts oscillating. Do the oscillations damp out and go away? That's stable. If there are no oscillations at all, if it just very smoothly returns to its trimmed airspeed without any oscillations at all, that's called overdamped stability. But if the oscillations keep occurring and get bigger and bigger, then it's dynamically unstable. So it can be statically stable and dynamically unstable. I don't think there's any way to be statically unstable but dynamically stable. So how do we get pitch stability? Airplanes are statically pitch stable when the rear wing provides a restoring force opposite to the perturbation. So this means that the rear wing needs to be more effective than the forward wing. It needs to have a higher lift curve slope. This implies that the front wing always needs to be more heavily loaded than the rear wing. In a conventional airplane, the front wing will be carrying the vast majority of the load of the airplane. Generally, the tail will have a downforce, but not always. There can be times at aft CGs where there will be a small up force. But if you take a look at the area of the main wing and the area of the tail, the force per unit area on the main wing will always be much higher than the force per unit area on the tail. This gives you the pitch stability that you need. In a canard, the same rules apply. The front wing needs to be more heavily loaded. And that means that the canard has to be much more heavily loaded than the main wing in order to assist in creating the pitch stability. It also means in any plane, again, conventional or canard, that the center of gravity has to be ahead of the center of lift of the airplane as a whole. So as an example, on the Canard airplanes that we fly, they're only about 15% of the total wing area, but they carry anywhere between 25 and 33% of the load. So you can see that it's substantially more heavily loaded than the main wing. And the reason for that is that as you, let's say, hit an updraft, a gust, some perturbation, you want the lift coefficient on the front wing to change less than the lift coefficient on the rear wing. And that will cause the front wing to not try to go up as much as the rear wing will. That'll cause the back of the airplane to go up more than the nose of the airplane, and that'll return you back to your trimmed airspeed. So we get to roll and yaw stability. Static stability, again, does the plane want to return to the direction it's pointing after a yaw perturbation? So you punch a rudder pedal, the plane yaws to one side or the other, and you take your foot off the rudder pedal. What does the plane do? Does it want to return back to pointing the direction it was going before? Does it want to just sit there flying sideways? Or does it want to swap ends? Obviously, yaw stability is important. Otherwise, you really have to be on the rudder pedals incessantly in order to keep the plane from trying to go in some other direction than it's pointing. You can see in the picture on the right that dihedral is generally added to airplanes because it will also help with lateral stability in causing a greater angle of attack on the downwing and a lesser angle of attack on the upper wing, which will help raise the wing that has lowered due to a gust or perturbation of some sort. Dynamic stability, again, as with pitch stability, if there's an oscillation, do the oscillations get bigger or do they get smaller? Now, roll and yaw are interconnected, and I'm sure everybody has felt this, that you can kick your rudder and the plane will have some roll effect as well, or you roll into a turn and the plane will have adverse yaw and try to turn in the direction opposite to the direction you want it to. This results in a Dutch roll effect, this interconnectivity, and it also causes a spiral instability. And generally, you get one or the other. you're not going to be able, it's very difficult to have both yaw and roll stability. Most of the time, you will want yaw stability and are willing to put up with a little bit of roll instability because the roll instability is slow, especially in high performance airplanes. If you just let go of the stick or the yoke and you just don't have your autopilot on, eventually the plane will roll off to one side or the other and just start increasing in a spiral dive. But it takes a long time. This doesn't happen in a couple of seconds. This could take 10, 15, 30 seconds, a minute, a couple of minutes sometimes. So we're willing to put up with the roll instability because it allows us to have the yaw instability that is more important. And the dihedral effect and the sweep of the wings both contribute to this stability. So let's talk a little bit about winglets. There's a lot of misconceptions about what winglets are and what they're for and what they do. So the original purpose of winglets, and the reason you see them on commercial airliners, as developed by a guy named Whitcomb back in the 60s, was to decrease induced drag without increasing the span. So go back and think about our discussion earlier about having longer span wings to decrease the induced drag. The problem is you make the wings a lot longer, they're creating more lift, which means that your spar needs to be stronger and it needs to be heavier. And you probably also need to decrease the chord because you only want the wing to be a certain size. And that then leads to Reynolds number effects. So this guy Whitcomb said, well, what if we just tilt the tip of the wing up? Can we then decrease the induced drag without increasing the span? And the answer was, yes, we can. If you orient the winglet correctly, you can actually remember that the lift is always perpendicular to the flow over the, in the direction that the air is going over that airfoil, and the drag is perpendicular to it. Well, because of the 3D effects of the way the air flows near the tip of the wing, you can actually have airflow going over the winglet that produces a tiny little bit of thrust. And that tiny little bit of thrust is negative, essentially negative drag. So what you're doing is you're decreasing drag by having a winglet on the tip of the wing. And it provides about 1/3 of the effect of lower drag as increasing the span of the same length of the winglet would. So if you just took that winglet and flattened it out, you'd get 3 times the efficiency gain, but you'd have to make your spar stronger. You'd have to have more space to park your plane. There's all sorts of other issues associated with it. So this was a different way of creating a drag reduction without increasing the span. And generally, if you're flying at the best lift over drag speed, so the place where the induced drag and the profile drag of the airplane are equal, and this is generally where commercial airliners fly, you can get a 1 to 3% drag decrease. For our airplanes being Canards, the best L over D speed is about 85 knots. Nobody flies around at 85 knots because that's not why you bought a plane that can go 170 knots or built a plane that can go 170 knots. So the question is, well, then why do we have winglets if we're not using this functionality? And the answer is, well, Canard airplanes still need directional stability. We still need a vertical stabilizer. And if you take a look at the way these planes are configured, there isn't a whole lot of space directly behind on the fuselage to put a vertical stabilizer that's far enough behind the CG to have much of an effect. But if you sweep the wings, now you can put your vertical stabilizer reasonably far aft of the CG, and you can see that you're going to get a substantial amount of directional stability out of these vertical stabilizers. They really do nothing for efficiency or drag reduction, and that's, as I said before, because we don't cruise around at our best L over D speeds. The other issue is the wing sweep, and people go, oh, you know, that looks cool, looks like a jet. And so, yeah, that's nice. But the reason the wings are swept mostly was just to get the winglets far enough back to be effective without having to be huge. If you talk to the folks, Mike Melville and Vic Rutan, who did the flight testing, the original Long Easy used Very Easy winglets. And the Very Easy is a smaller plane. And Bert tried to use the Very Easy winglets on the Long Easy, and they were way too small, and the plane had really poor directional stability. And they very slowly increased the size of the verticals over 5 different versions to get to the current size. But originally, according to Mike and Dick, the plane was perfectly happy to fly sideways if it got perturbed one way or the other. So now we get to the meat of this, which is, you know, everybody goes, oh man, Canards, well, not everybody, but a lot of people, especially Canard owners, like to believe that their airplanes are substantially higher performance and higher efficiency than conventional aircraft. And so the question is that really true? And the question is, well, all else has to be equal in order to be able to have a one-to-one comparison, right? And so what's all else? Well, fuselage size and shape. Is it a side-by-side airplane that you're comparing it to? Is it tandem? Do you sit straight up? Are you laying down? What's the wing size and area? Do you have fixed or retractable gear? How much power do you have? And do you have a fixed pitch or constant speed prop? So you kind of need to evaluate like versus like to the level that it's possible to do so. And because of the configuration.
Kind of like in Formula One.
Yeah, right. You know, you want to be as close as you can in order to be able to have a comparison. Otherwise, you don't really know which things you're comparing. So what's the closest thing to a Long Easy? Well, maybe Glass Airs, Lance Aero 235s, Legacy, Tango 2, the tandem RVs. For Cozy Mark 4s, 4-seaters, RV10s, Wheeler Express, Lance Air 4s. There's no question that Canards are high performance airplanes. They're very efficient and they have great performance. But is it more? Is it better? And to the extent that you can actually measure and compare like versus like, there is no substantive difference in efficiency and performance. You can take a look at airplanes that have similar engines, similar sizes, carry similar weights, and they basically perform about the same. So the answer is they are high performance planes, but they're not higher performance than conventional aircraft. So what are the overall advantages then? And the advantages are that they have very good stall and spin resistance, and that's about it. Generally, Canard owners don't like me to say this to them when I give this presentation. They're like, you're disabusing us of our notions of wonderfulness.
Klaus would fight you.
Yeah, well, there are airplanes there are 2-seat airplanes with similar engines to Klaus's that are just as fast as he is. So, you know, he can argue all he wants, but the answer is that it's about the same. Now,
I've never seen a Canard glider.
and that's a good point. There have been a few, and Bert designed Solitaire, and it was a decent enough plane. But because of some of the issues with Canard airplanes not being able to use the main wing's maximum lift coefficient, you actually have to make and because it also operates in the downwash of the Canard, and we'll get to that a little further down, it turns out that it's very hard to make a Canard glider that is as efficient as a conventional glider.
Yeah, I think the Silhouette and the one you were just talking about, Solitaire. Would make a good comparison, say for the engine on one and not on the other.
Yeah. Yep.
The difficulty is overcoming that need to keep the stall resistance.
Exactly.
Pays a penalty.
You do. You pay a penalty from that, and that your main wing has to be larger than it otherwise would be. And so whatever drag benefit you're getting out of having the canard lifting, you lose in other areas, and you'll see that in some of these further slides. So relative efficiency, performance, and what was the third thing? Oh. Capability.
Quick question. How do lifting tail conventional planform aircraft compare? Say we take the downforce tail. There are designs that have been flown that have a lifting tail behind the main wing. How do those compare?
So there is controversy as to what the most efficient configuration for an airplane is. But if you think about airplanes as a continuum, generally airplanes have two lifting surfaces. You got one in the front, you got one in the back. You look at something like this picture of a Cozy Mark IV, the front wing is relatively small, the rear wing is relatively large. Then make the front wing a little bit larger and the rear wing a little bit smaller, and keep doing that. You eventually get to something like a Quickie, a Q1 or a Q2, where the wings are approximately the same size, or Proteus, where the wings are, the front wing is just a little bit smaller than the rear wing. That's a tandem aircraft. Keep doing that, and just make the front wing a little bit larger, rear wing a little bit smaller, and just keep along that continuum, and you eventually get to what we see as conventional planes. Well, if you make the rear wing larger than a conventional plane, but nowhere near as large as one of these canards, you'll end up with a rear wing that needs to produce lift in order to keep the plane balanced. And so the answer is that it's not like there is some break between these types of airplanes. It goes all the way from single lifting surface flying wings to tandem surface wings with a tiny wing in the front and a big wing in the back, to the other way around, a big wing in the front and a tiny wing in the back. And then you get into things like three surface aircraft, like the Piaggio Avanti or things of that nature. And there are a number of analyses that have been done that seem to indicate that a perfectly designed three-surface aircraft will be the most efficient configuration. But that's in analysis, and again, you would need to create two aircraft that in every other way are identical, except for that third surface, and then compare them in actual use. And because making airplanes that are identical except for this one parameter is very difficult, we don't really know what the most efficient configuration is. It's fairly, I would make the argument that from a pure efficiency standpoint, if you take a look at what airliners do, because the largest cost they have is fuel. And so if they're willing to throw winglets onto the wing in order to pick up 1%, they'd be willing to pick up 1% by changing the configuration of the plane if they thought that that would get them 1 or 2 or 3% more efficiency, and they don't do it. So I think we've got enough heuristic evidence to indicate that conventional configurations are, if not better, at least no worse than a Canard. And the quote unquote optimal configuration is unclear. So relative efficiency, performance, and capability. You need to have deep stall resistance in these planes. And in order to get that, the main wing has to be larger than optimal so that it will never stall. And so the Canard has to stall first. Deep stalls are dangerous conditions because they're incredibly stable and they're almost impossible to get out of. And so it's something we really need to avoid. That requires that the main wing never reaches the critical angle of attack, even when you're at your aftmost center of gravity position. And so that implies that the main wing has to be larger than if you were allowed to reach the critical angle of attack. So the other issue going on here is that you have a Canard downwash effect on the main wing. And this is something that, of course, people don't think about when they're saying, oh, but the front wing is lifting. It's like, yep, the front wing is lifting, and that's a good thing. But because it's creating downwash, it's actually lowering the angle of attack of the center section of the main wing. And so therefore, again, the main wing is not being as efficient as it could be because you need to have the main wing be a little bit larger and you have a suboptimal lift distribution. An optimal lift distribution is approximately elliptical, and you can't get that if the main wing is operating in the downwash of the canard. So both
Can you move the canard? Can you move the canard far enough out of plane to eliminate that?
So that's a good question, and the issue is that the downwash effect occurs in an area. If you basically draw a circle that is the span of the canard, and in these planes it's about 12 feet. If you draw a circle with a diameter of 12 feet, inside that 12-foot diameter is where that downwash effect is going to exist. So unless you were willing to put the canard 12 feet above or below in this case, 6 feet above or below the main wing, you're not going to get rid of that. And of course, nobody's going to put their canard 6 feet above the airplane. If for no other reason than it would look ridiculous, it would have a ton of structure to try to hold it there. And all that stuff would probably create enough drag and structural issues that you wouldn't go there. So that's the problem with trying to get, you'll see some canards where they've raised the canard a little bit above, and oh, well, that gets the downwash to flow above the main wings. Like, yeah, no, it doesn't. If you've got a 10-foot span canard, you need to have that canard 5 feet above the main wing for the downwash not to be affecting it, and nobody does that. This is another issue that creates a suboptimal effect of canard aircraft. So then you get to hey, but both wings are lifting. Why isn't that a huge advantage? I'm going to have more, the traditional aircraft has to create more lift. And so therefore there's going to be more drag. And you get back to the all else being equal, right? You've got the downwash from the canard. You've got the requirement for canard stalling first. And you pretty much end up in the same place overall from a drag standpoint. So there's just not a huge difference one way or the other. So what are some other issues with efficiency, performance, and capability? Well, canards generally have relatively poor short and soft field performance. All high performance planes, where high performance in this case means high speed cross-country cruising airplanes, they suffer in these areas, but canards more than most. They have relatively small main tires, and they're susceptible to bumps and ruts. Tiny nose tire, same issues. For all of Bert's brilliance, landing gear design was not his strong suit, and the weak nose gear strut and connectivity there is problematic on rough fields. The main gear is also suboptimally robust. That's my wording. The other thing is that due to the way the nose gear is, the geometry is, and the fact that if you hit a bump with the nose gear and it moves backwards, it also moves up. And you can see the red arrow there. And so what happens is if you hit a bump on a rough runway, you actually lose angle of attack. And so that makes it more difficult to rotate. There's no prop wash over the horizontal tail to assist in controllability at low speeds. There are some canards that operate off of grass fields. It's done in Europe some amount because they've got some really nice grass fields that are basically golf course putting greens. If the field is hard packed and the grass is short enough and you got a long enough field, then yeah, you can operate off of grass. But these are, nobody's going to land a canard on a sandbar. But on the other hand, nobody's going to land a Lancer 360 on a sandbar either. So in that sense, they have the same issues that all high-speed cruising airplanes have, plus a few other issues.
What about pitch sensitivity?
The Canard airplanes tend to be more pitch sensitive, but not twitchy. It takes a little while to get used to them, so you don't end up with PIOs. We'll talk a little bit about that here. perfect question for this slide. So we'll go through the bullet points. Relative field length has to do with rotation. You need to get to enough of a speed where you can lift the canard in order to get the main wing to an angle of attack where it'll start flying. All high performance planes use more runway than slower planes. The wings are smaller and they have higher stall speeds. It's just an innate issue with high performance planes. But the canards have the added disadvantage that the forward wing must create substantial lift, more than flying loads, to rotate around the main axle. Because it's not rotating around the CG, it's rotating around the main axle, which is further aft of the CG. This leads to PIOs on takeoff with less experienced pilots. Every time I transition somebody into a plane, the first thing that happens is they'll pull, they'll start rotating, and then they'll over-rotate, and then they'll push, and so you end up doing this on the first couple of takeoffs. It doesn't take very long to get to the point where you understand that after pulling enough to rotate, you relax the back pressure a little bit, and then you're fine. But it does take a couple of examples. Now, Mike Melville, my hangar mate, moved the main gear aft 1 inch on his airplane because he wanted to be able to have the plane sit on the ground without retracting the nose gear. Most of the time, you'll see canards with their nose gear retracted so that they don't fall over backwards when the people get out of them. Mike moved his gear aft so that he could let the nose gear sit on the ground. But he will be the first to admit that that made his plane even more difficult to rotate, that he needs a little bit more runway than most long easies because he's trying to get the nose to rotate around the axle until the main wing is actually lifting. Then you're operating around the CG, and that's why you need to then relax the back pressure a little bit. So another question I get asked about canards is, hey, why don't we use angle of attack indicators on these things? You know, they're great on conventional airplanes, and you fly the ball and keep the airplane in the right place, and you don't care what your indicated airspeed is, you don't care what CG you're at, you don't care how the airplane is loaded or whether you're in a turn, and keeping track of how your speed changes in a 45-degree bank. You just fly the angle of attack. And as long as you're at the right angle of attack, you won't stall the plane. The problem on canards is that you have a slotted flap, an elevator, on either the GU or the Ron's canard. And so when you deflect that flap downward, it moves the lift curve slope and increases the lift coefficient, also changes the drag coefficient, but we don't care about that from angle of attack standpoint. And so the movement of the canard then affects the main wing's angle of attack and airspeed. So you can measure the main wing angle of attack in order to prevent deep stall, but in order to calibrate the angle of attack gauge, you'd have to stall the main wing to know where it stalls. Well, we just decided before that deep stalls are really bad. You don't ever want to stall your aft lifting surface, whether it be on a conventional plane or a canard. It's dangerous when you get into a deep stall, and T-tailed airplanes will sometimes have this issue where if they get into a situation where the tail is operating in the wake of the stalled main wing, you can't recover from a stall. So you can have a deep stall in a conventional plane as well. Stalling the aft surface is a bad thing. And the problem is that on canard airplanes, the lifting surface that you care about stalling is the main wing, but you can't calibrate your angle of attack indicator because you're not willing to stall the main wing in order to do it. And you don't care about stalling the canard. It's fairly obvious when the canard is stalled, it'll just bob a little bit. And since you can do anything in the airplane while the canard is stalled, when I was doing my phase 1 testing, I did 60-degree bank turns with the canard stalled, and it felt like I was in my dryer, whizzing around in circles, bobbing in this tiny little turning radius. But there's no danger to it because you're not stalling the main wing. So you still have your lift, you can maintain altitude, and you have full roll control because your ailerons are not on a stalled lifting surface. So the answer is you don't need an angle of attack indicator, and you can't calibrate it, so you couldn't use it. So back a little bit more about angle of attack indicators on the Canard. So then people said, well, just put the angle of attack indicator on the Canard. At least then you'd know what your angle of attack of the Canard was. And the problem there is that you have this flap on the Canard. And when you change the flap position, which is your elevator, you're changing the effective angle of attack of the Canard. The relative wind may be in exactly the same place. Your chord line is different though, because you've changed the camber of the airfoil. And so your angle of attack is changing, but it's changing because your elevator is moving. If you hard mounted your angle of attack indicator to the leading edge or underneath the Canard, it wouldn't see that your elevator has changed the effective angle of attack of the airfoil. So whether on the main wing or on the Canard, the angle of attack indicator is pretty useless. So let's get to a list of some aerodynamic modifications that people have made to airplanes and whether those are good or bad or indifferent. This is an airplane that was based on a long easy. It was at Oshkosh 2 years ago, and I think may have been there before. It had an extremely long nose. This airplane actually crashed about 1.5 years ago, and the pilot was killed. Apparently, it had some sort of a flutter event, and one of the wings ripped off. But my point in presenting this was just the incredibly long nose on this plane. And so this plane would have had lower directional stability. We talked about the winglets providing directional stability for these planes. And the reason they do that is because they are surfaces, vertical surfaces, aft of the center of gravity. Well, the nose of this plane is a vertical surface very far forward of the center of gravity. Anything forward of the center of gravity is destabilizing. And so when you put a long nose on a plane like this, you're decreasing the directional stability of the airplane. Now,
and you'd have proverse weathercock and a crosswind.
Yeah, I mean all sorts of directional issues. Basically the nose of the plane is working in opposition to the vertical tail, and who wants that? On other airplanes that I have flown that have either smaller winglets, we'll get to that, but a long nose. I've got a long easy that I maintain that has a nose that's about 30 inches longer than the stock long easy nose. And it has noticeably lower directional stability, especially at low speeds. This plane will also have lower pitch stability for exactly the same reason. You're adding surface area, horizontal surface area forward of the CG. So you are then going to decrease the pitch stability of the plane. You're also going to lower the deep stall resistance of the plane because you're adding surface area forward of the center of gravity. In this case, this is an extreme example. Very, very few people ever do anything this extreme. And I think the person did it because it's a jet and they wanted it to look like a jet, I suppose.
Just advantage and fineness ratio for drag reduction, or just cosmetics, really?
Cosmetics. There is zero. Well, there is an awful lot of electronics in this airplane as well, and they may have thought they needed more space. But fineness, the lowest drag shape has a 4:1 aspect ratio.
Yeah. Look at the wheel pans on a modern RV. That's exactly the lowest drag shape. Yeah.
Exactly. The RVs, the Sam James wheel pans for Canards and RVs. I mean, that's the shape.
Or the bluefin tuna.
Yeah, exactly. Bluefin tuna are not 40 feet long and 1 foot in diameter. So again, this was not done for aerodynamic reasons, and if anything, this had detrimental aerodynamic effects. Some people like to remove the lower winglets on these planes or make the upper winglets smaller. That also leads to lower directional stability, which is verified by flight testing. and also lowers the deep stall resistance of the plane because the lower winglet is actually helping to reduce span-wise flow, and increased span-wise flow decreases the ability of the main wing to maintain lift. And so again, more detrimental issues. Now in this case, at least it does reduce drag a little bit. You might be a little bit faster by having a smaller upper winglet. Nobody has verified a speed increase A to B comparison with just taking an airplane that had lower winglets and then removing them. So, you know, if there's enough of the drag reduction to matter, it's kind of in the noise.
Has anybody tried the new, like the 737 MAX winglets, where they're a very small trailing edge, lower winglet, and then the conventional blended winglet on top?
I don't know of any Canards that have done that. I've assisted with the design and construction of 2 or 3 different airplanes with blended winglets, and that's a different presentation. There are 2 airplanes that had regular winglets that installed blended winglets and did A to B comparisons. The other folks that have done blended winglets—
Reader's Digest on that?
I'm sorry?
Reader's Digest results on that?
Yeah, interestingly, the Reader's Digest version is that the first airplane, which was Jack Morrison's E-Racer, which was an 0540 supercharged plane, it was a monster. And he wanted blended winglets. And I told him, you don't want blended winglets. And he says, yes, I do. I want you to help me do it. I said, you don't want blended winglets. You won't get anything out of them. And he said, but I want them, and I want you to just help me make them safe. So I did that, and he installed them. But I told him, here's a bunch of data I want you to collect first before you do it. And he did. He collected a bunch of data. Then he did the blended winglets, and then we collected a bunch of data again. And to my extreme surprise, he actually had a substantial drag decrease. Then Chris Esselstyn on an 0540 powered Cozy Mark IV did the same thing. And he installed blended winglets. And I had him take data before the blend and then after the blend, and he got exactly 0 change. So then the question comes
similar chord and span?
Exactly the same. In both cases, they took the existing winglet, cut out the area between the wing and the winglet, and put a blend in it.
Interesting.
That's it.
Not how I do it, but okay.
My theory for why Jack Morrison picked up the speed and Chris didn't is that on an E-Racer, Chirl Dickey, who designed the plane, decided that he didn't like the fact— if you take a look at this, you can see that the winglet is set back about 4 or 5 inches from the leading edge of the wing. And he didn't like that. He thought that looked crappy. And apparently Velocity thought it looked crappy for a while too, because some Velocities have the leading edge of the wing and the winglet coincident. Chirl Dickey did that on the E-Racer. That's really bad aerodynamically. There's a reason Bert put the winglet 5 inches aft, and it's so that the thickest part of the wing and the thickest part of the winglet aren't in the same place, and your intersection drag will be lower. So I think what happened was that that Jack Morrison with the E-Racer was starting from a crappier place than Chris Esselstyn was starting from. And so putting the blend in got rid of the intersection drag problem on the E-Racer. And the blend itself may or may not have been the thing that picked up or that got rid of the drag. It was the fact that you didn't have that intersection drag anymore. On Chris's plane, he left the winglet at that 5-inch offset, which I wouldn't have done because
why blend?
Yeah, why blend? So he put a very pretty blend in there and then got exactly 0 performance increase out of it.
Welcome to air racing, by the way.
What's that?
Welcome to air racing, by the way.
Yeah.
If it looks good, it's not necessarily fast.
Yeah, that's and I give both Jack and Chris a lot of credit for trying to be safe in making major structural and aerodynamic modifications to their planes, and in being willing to experiment, because that's how you learn.
Hey, the scientific method is everything.
Yeah.
Nice.
And but back to this modification, smaller upper winglets, at least there is some drag reduction in doing this, but you do lose directional stability. So,
Sorry to drag you off topic.
No, that's okay. I'll talk as long as you guys want to listen. So other aerodynamic modifications, and of course I just talked about this. This is a picture of Jack Morrison's blended winglet. So you can see the leading edge just going straight from one into the other. The picture on the left is that jet Long Easy-like airplane that also had blended winglets, plus some weird thing up at the tip that looks kind of dragonish, but who knows what that was there for. So this was done for drag reduction purposes. Jack's plane was the only successful A to B comparison. This has always been done in concert with a lower winglet removal, which, as described on the previous slide, is going to reduce the deep stall margin of the plane. You may or may not be familiar with an aircraft called the Raptor, which is an airplane designed by Peter Muller, which is a very large Velocity XL-ish plane that also has blended winglets on it. But it, in fact, is the only one with blended winglets that also has lower wing tip fences on it, just at the inner tangency point of the blend on the wing. It has never flown without them, so we don't know what the difference would be. It's barely flown with them. But in any case, on all the other Canard airplanes that have put blended winglets on, it's always been without the lower winglet. This is the original Aero Canard, which is essentially a very, very slightly modified Cozy Mark IV. This airplane has dihedral in the Canard. I have no idea why people do this. There have been 2 or 3 people that have done this on an Aero Canard, 1 person on a Cozy. I don't know if I've ever seen it on a Long Easy. Maybe they're looking for some roll stability increase. I have no idea. All I know is it makes fabricating the Canard harder. It makes the control system more difficult. Who knows why people do things. No measurable difference to anything else. Other aerodynamic modifications that people have made to these planes is putting a tip plate on the Canard. This is area ahead of the CG. It lowers your directional stability. It may or may not affect deep stall, because if you increase the effectivity of the Canard by equivalent to increasing the span or area, then you are increasing the angle that it can get to, which means it can get closer to stalling your main wing. There have been some Canard span changes. Long Easies and Cozy 3s started out with GU Canards, and many people switched to Ronce Canards because the GU has terrible contamination effects. If they get dirty or get rained on, they have very large trim changes. The Ronce Canard does not, and so a number of people have changed, but in changing to the different airfoil, they needed to, because of the better effectivity of the Ronce, they needed to shorten the Canard. The Ronce Canard on the Cozy Mark IV, which was the original and only airfoil used on the Cozy Mark IV for the Canard, had a 6-inch span decrease after some deep stall testing that the designer Nat Puffer did, in which it was, he got into some incipient deep stalls because the Canard was too effective. And the part of that is because of the increased width of the fuselage, and because the fuselage lifting effects forward of the CG are nonlinear, it was unclear what effect that was going to have. Increasing the span moves the aerodynamic center forward, which decreases pitch stability, decreases deep stall resistance, and requires moving the CG range forward. So I tell people, if let's say they want to fly with 200-pound people on a regular basis, I tell them, yeah, you can leave the Canard at the original length, but you should move your CG range forward by 1 inch to 1.5 inches because you're changing where the aerodynamic center of the airplane is. Some folks have tried semi-symmetric winglet airfoils with the intent of reducing drag at high speeds. Chris Esselstyn actually did that when he did his blended winglets. So there kind of was two changes. I spent a bunch of time working at Scaled, and when I was there, I asked the chief aerodynamicist there what would happen if you used a symmetric winglet airfoil instead of the same airfoil that the main wing uses. And he said, well, could go either way, depending on 23 different parameters and factors. So it's complicated. As I said earlier, the wider fuselage of the Cozy Mark IV decreased the pitch stability, decreased deep stall resistance. Some people have increased the Cozy Mark IV fuselage width because it's called a Cozy for a reason. I am 5'6", I weigh 150 pounds. I fit in the plane just fine. But if you're 6'3" and weigh 220 or 230, and you want to fly with a friend who's the same size as you, you are going to be crammed in there pretty tight. So some folks have increased the fuselage width by anywhere from 4 to 6 inches. And what I tell them is that will decrease your pitch stability, will decrease your deep stall resistance. They say, how much? I say, I have no idea. Somebody who does this is going to have to go out and test their airplane and determine whether it's even measurable or whether it's a big deal. And right now there is a 6-inch wider Cozy Mark IV that has just started its flight test period. And so I have been beating on the owner for about 10 years that he better collect real data on this thing so that we can actually publish something, because the other people that have done this that I've asked about refuse to tell me what their stall test results were.
Now, the decreased deep stall protection is just because of the greater lift generated forward of the CG?
Exactly. If you can get to a higher angle of attack because of the wider fuselage, very far forward of the CG, then you might be able to get the airplane high enough to get the main wing to stall. And
I'd have a drag chute installed before I tried that.
Well, there are a number of things you can do. And the main thing you can do is you start testing towards the forward end of your CG range and slowly work your way back in 1/4 inch increments. And when the plane starts acting a little squirrely, that's where you stop. And then you move your CG back 1/4 inch further forward and say, that's your rear limit. And there are other things you can do. What Nat Puffer did, and I think one other person has done this, is they actually installed a 100-pound movable weight in the plane and put a hole in their front seat back. And they were able to substantially change the CG of the airplane by moving 100 pounds forward 6 feet inside the
Wow. Holy, yeah, that'd be big.
That would do it, right? You know, if you get your CG much further forward.
But if it's, hey, the airplane isn't going to know which way to point forward unless you do something like that. I've debated doing something similar on my modified Cassett Formula One racer, just because it goes fastest with absolutely neutral stability, but it's not much fun to fly.
Yeah, it's miserable. But no, the airplane in a Cozy Mark, well, any of these Canards, Velocities have had deep stalls, Long Easies have had deep stalls, Cozy Mark IVs have had deep stalls. They're incredibly stable situations in which you are in about a 45-degree angle of attack, but you are pretty much perfectly level. And so what that means is that your forward speed and your vertical speed are pretty much about the same. And they're both about 45 miles an hour, give or take. And you're in a deep energy well. And the only person I know of who has been able to get out of a deep stall in one of these planes is Mike Melville. He started the deep stall at about 13,000 feet, and they were doing some testing with a very aft CG, 3 inches aft of the aft CG limit for the plane. And they got the plane into a deep stall, and Mike tried everything. He says now that he should have jumped out, but he recovered after losing 12,000 feet by rocking the rudders. And because of
to roll off.
Yes, because of the pitch, because of the roll yaw coupling, he was able to get the plane to rock and eventually go over the top, point nose down. And as soon as it picked up some airspeed, it's flying again. And he was able to recover at about 1,000 feet over the supermarket in Mojave.
Not for the faint of heart.
No.
It seems like there was a case off the coast of Florida back in
Yes.
the 80s where a Canard airplane had the same problem and the guy couldn't decide whether to bail out or not, and he just wrote it down.
Yes,
It got to, I don't remember what company it was, Velocity or
that was a
somebody else.
Velocity. Yeah, that was a Velocity, and he did write it down. And everybody who has chosen to ride one down has survived. You hit the ground hard. He went into the water, so he was uninjured. The two Cozy Mark IV deep stalls that I know about, three actually, there were broken ankles, injured backs, but no fatalities.
Hey, doing the math, 45 miles an hour on a 40-degree downline, that's the same energy profile as a Cirrus under canopy.
Yeah.
800 feet a minute is my guess.
Except, well, it's about a 3,000 foot per minute descent rate in the deep stall.
Really?
But the issue is just that you're sitting on the bottom of the airplane. In a Cirrus, you've got a 26G seat under you.
Yeah.
So deep stalls are survivable. The fatality that occurred in Velocities was because it was an inverted deep stall caused by wake turbulence. And obviously inverted is a different story. The other deep stall fatality that occurred in a very heavily modified Cozy Mark IV was because it had a forward hinged canopy, and the pilot tried to eject the canopy when he was in the deep stall over Long Island Sound. The canopy came back and impacted him in the head, and he died from blunt force trauma, not from impact with the water of the airplane. So that's it. These are all the references that I used. I stole as many pictures as I could from people who knew what they were talking about and what they were doing. The first reference here, the See How It Flies website, is really a wonderful, wonderful reference for understanding airplanes in a slightly mathematical way, but the explanations are really good. I like it. And there's almost nothing on that website that I've found that I disagree with, that I say, no, that's not how airplanes work. Whereas a lot of websites, they're like, yeah, no, that's not how it works. NASA, Wikipedia, Bold Method has some, those were the pictures that had the blue in them. Those are good. There's just a lot of websites out there that are really, really useful for explaining airplanes in general. The Apollo Canard website, I'm really sorry that guy never finished his plane, but he's got a lot of really good explanations for how canards work and pictures of things and why he did things somewhat differently than the way Bert did. And then, of course, there's Aerodynamics for Naval Aviators, which is, of course, an excellent reference. And this is me. I'm always available. Email, phone, I'm into Hatchapy. As I said, I run the Cozy Builders website. My website for business is Burnside Aerospace. And Kevin isn't here, but he's up in the San Francisco Bay Area, and he helped me out with reviewing this thing and making sure that I wasn't making a total fool of myself. So, anything else? We've gone.
I have a question. I remember back in 2003 when they were doing the 100th anniversary of the Wright Flyer that they said it was a bitch to fly. Is that because of the Canard configuration on it?
It was because it was unstable in pitch. Whether because of the Canard configuration or something else, or they didn't quite understand how to ensure pitch stability in an airplane, it was unstable in pitch. And so it just it took constant pilot inputs in order to keep the thing level. It didn't take very long before both the Wright brothers and everybody else started understanding how you get static pitch stability in airplanes. And so you see the later Wright Flyers, even just a couple of years later, they had totally figured it out, and the airplanes were stable. But the first one, if you calculate where the weight is, and where the center of gravity is, and where the center of lift is, the center of lift is pretty far forward of the center of gravity, and that's a problem.
Excellent.
I just PIO'd the simulator, and the biggest biggest challenge on the Wright Flyer simulator was getting fast enough to get roll control because wing warping sucks.
Yeah, I'll bet. I'll bet.
But you can PIO it fast enough if you try really hard. Why are canards almost universally pushers?
What?
Should I start?
Yeah, it's coming near its end.
It's mostly a weight and balance thing. If you start saying, well, I mean, you kind of want everything that can change to be on the CG, right? You want your pilots, your passengers, your fuel. You want all of that on the CG, just so that your CG doesn't move when you have people getting in and out of the plane, or when you add or subtract fuel. So you start creating a configuration of a plane, and you start saying, well, I need vertical tails, and I need the CG to be in a certain place. If I put the engine up in the front, I can't get the CG in a reasonable place. And it's not that it's impossible, it's just that you end up with an extremely different looking airplane. You end up with a canard that has to be right up next to the engine. You end up with a tail. You could end up with a tail that is long with a vertical stabilizer on it. I think there was a three-surface plane, Eagle.
The Wren, it was a modified 182 with a canard with a.
But there was one
movable
that was an experimental plane that was designed as a three-surface.
It was the Eagle.
Yeah, the Eagle, and it had slightly forward swept wings in order to take into account where you were having to put people and where you had to put the fuel. So mostly it's a configuration thing.
You also had the Grizzly with the tracker.
Right, that was another three-surface aircraft.
Three-surface, and the Quickie is even though it's equal area, it's a tracker.
Right, and so you can see you can do this, but you end up with different configurations. So I think the reason that most of these planes are like this is because that's how Bert started the design, and everybody just sort of modified from there, and it was something that we knew worked.
Hard to argue against the performance of a Piaggio.
Yeah, absolutely.
Which is not plastic.
No.
Which shocks most people who don't know. But yeah, you're looking at 400 knot speed on King Air fuel burn with the same cabin as a Hawker 800.
Yep. Yeah,
but they are runway lovers. So.
Yep.
I have a question.
Sure.
How much do you know about Dan Card's Mermaid? And he was really good friends with Bert Bertan and all those guys.
Dave who?
Dan Card.
I'm not familiar with him or his plane.
He ran the weather observation during Voyager flight.
Ah, okay.
Thank you, Bruce.
I'll bet Bruce Evans just stopped by the hangar today, and I'll bet he knows Dan.
I have a question. I know the Wright brothers had some kind of a canard, but was Bert Rutan the first one who actually put on airplanes and kind of almost mass produced it?
No, there were actually a number of canard airplanes. There were actually a couple of fighter airplanes in World War II that were canards. They weren't successful. But they were developed and they were test flown. No, Bert was not the first. He was the first to popularize the idea and to create successful canard designs, but he wasn't the first to try it.
Okay.
Mark, I'd like to go to more of a general question. On your stall slide, you had the airflow visualization, and it looked like there was quite a bit of reflex in the airflow after the trailing edge in a stalled condition.
Is this the slide you're talking
Could
about?
you translate that as a loss of downwash?
Are you're talking about the slide?
Yes, I am.
Yeah.
It looks to me like you lose most of your downwash.
It does look like that, doesn't it? And I think that's due to the turbulent vortices over the top of the wing. I am not enough of an aerodynamicist, not any of an aerodynamicist, so I'm certainly not enough of an aerodynamicist to explain what's going on here. You can still see some upwash ahead of the wing. You obviously see the separation in the vortices and eddies. But, you know, I'd never actually noticed that once you get about one chord length behind the wing, you all of a sudden start seeing the air move up substantially. And I would guess that's just because of the extreme pressure loss and energy loss in the air going over the top of the wing. So the pressure has decreased so much as you get back that chord length that the high pressure air on the bottom has space to move up.
I wouldn't be surprised if that picture went off another wing length to the right, that you might see it going back down too.
Oh yeah,
very possibly.
Absolutely.
Very possibly. I don't know what the rest of that wind tunnel.
That's the part that makes up. That's the part that composes the post stall lift component. Is move two wingspans to the right in that drawing, and there is a significant, at least on conventional NACA stuff. Anybody messing with boundary layer control on main wing to reduce the requirement for oversized main wing for deep stall resistance?
I am not aware of anybody trying anything, and the reason is that boundary layer control is really hard and really expensive. There's just nobody doing that.
No, micro VGs are pretty cheap.
Oh, you're talking about that kind of boundary layer control. The answer there.
Yeah, active boundary layer control. Yeah, the Air Force proved it worked, and
yeah.
the Air Force proved they couldn't afford it. Yeah.
Yeah, I thought you were talking about active boundary layer.
Oh, I wish.
So the answer is yes. If you have, let's say, a long easy or a cozy 3 or a very easy with a GU Canard, or actually even a cozy with a Rance Canard, there are VGs that you can put on both the Canard and the main wing that will allow you to reach a higher angle of attack because it will keep the flow attached over both airfoil surfaces. And in fact, Jim Price, who set the class 1C, I think, altitude record in a long easy of 35,000 feet, did so by doing a lot of testing in a university with VGs to figure out the optimal configuration. And he was able to lower the stall speed on his plane by about 7 to 10 knots. And by doing so, he was able to get about 3,000 or 4,000 feet higher than he otherwise would have been able to get with that plane. So the answer is yes. And I actually have plans for those VG positions on the Cozy Builders website. So anybody that wants to can fabricate a bunch of little VGs and stick them all over their wing and fly slower and land slower and have a little bit of increased safety at the low end at the cost of about 2 knots on the top end.
I think some people have even experimented with electrostatic functions for maintaining airflow over the wing surface.
Yeah, could be. There's a lot of ideas for that, but I don't think anybody's been successful at not having it take more power than just overcoming the drag would. And, you know, it just seems to be an extremely difficult problem, active boundary layer control. A lot easier just to make your wing a little bigger.
Infinite maintenance dollars fixes all.
Right. Yeah, if my wing has 5 extra square feet of wing area, there's no maintenance involved in that.
Yes.
So my wife is, if we don't have any more questions, my wife is telling me that it is time to go watch a movie
Oh,
and eat some popcorn.
well, I'm very sorry. I'm very sorry. This is Tim Cohn, and I'm very sorry to have been late to the show. I had a work trip that extended unexpectedly. Thank you for the presentation on the Canard aerodynamics portion, but also a great, excellent, just basic aerodynamics and why airplanes fly primer. I greatly appreciate your time and energy on this.
Well, I appreciate that, and I appreciate all you guys showing up. I know this is not the optimal methodology for transfer of information, but we do what we can. And so I appreciate you guys showing up and inviting me. It's been fun, and you know where to find me if you want to.
Great.
Thank you very much.
So much.
Thank you, Mark.
We appreciate it.
And Geneva, you probably want to take back host control, because otherwise.
I just did.
There she is.
Okay, great. Now I can leave and you guys can have your meeting, and I can go watch a movie. Thanks
Thank
a bunch,
you, Mark.
guys. Appreciate it.
Thank you, Mark.
Thanks a lot, Mark.
Bye.
What
Thank you
about
much.
people in Mojave that have interesting mustaches?
Well, that was very nice. Hello?
All right,
Business.
Diane, you want me to give you control?
Yeah, that's fine. I can't take it on my cell phone.